Let's listen to the supplemental problem 13.2. You can find this problem in the ECE202 ebook in the Chapter 13 supplemental problem starting on page 3. Given what's called a half-wave rectified sine wave with an amplitude of A and a period of t0, can you find the Fourier series? What I've sketched here below is the waveform for a half-wave rectified sine wave. And you can see here it's a sine wave with the bottom half chopped off. In ECE302, we're going to use this particular waveform to create a DC power supply. The sine wave has an average value of 0, but if you chop off the bottom, the average value now is no longer 0. In other words, there's an area under the curve for a period. We need to write an equation for f of t. This is still a sine wave. We can describe this as a sine of 2 pi times f. Now f is the reciprocal of t0. We'll call that f0 times t, and then the amplitude is equal to a. Now the waveform is non-zero between 0 and t0 over 2, and then it's going to be equal to 0 for t0 over 2 to t0. So two different values for our waveform. This particular waveform doesn't have even symmetry, odd symmetry, or half-wave symmetry. So we'll have to do our Fourier series from our basic definition. Recall, a0 is equal to 1 over t0, the integral over a period of our function. But our function is 0 for half the period. So all I'll do is take our integral from 0 to t0 over 2 of our function. And of course, then plus the integral from t0 over 2 to t0, but that's just the integral of 0, which is 0. Pull out the a in front. We have a over t0. Recall the integral of the sine of ax is minus 1 over a cosine of ax. So we'll have a minus 1. Here's our value of a, which is 2 pi f0. And then the cosine of the same argument, evaluated from our upper limit minus our lower limit. Plugging in for t0 over 2, and then plugging in 0. Get some cancellation. t0's cancel, the 2's cancel. I also have one more cancellation here. t0 and f0 is 1 over t0, so these two cancel also. I'm left with then a minus a over 2 pi. And then I've got the cosine of pi minus the cosine of 0. Well, the cosine of pi, which is the cosine of 180, is equal to a minus 1. And then I have a minus a plus 1. So I get 2 here, but the minus signs cancel. And that cancels with the 2 in the denominator, so I get a over pi. My value for a0. So the average value is what a0 represents, is no longer 0, as it was for the sine wave, but now is equal to a over pi. Our next term is a sub n. If you recall, that's 2 over t0 integral over the period of our function times the cosine of 2 pi n f naught t. Our function is 0 for half the period, so we're just going to integrate from 0 to t0 over 2. I've got a sine times a cosine, so we can go back and grab some of our trig identities. Recall that the sine of alpha times the cosine of beta is 1/2 the sine of the difference plus 1/2 the sine of the sum. We have 2 over t0. I can bring out the a, left with the integral then from 0 to t0 over 2. And I'll take this product, so it's going to be 1/2 the sine. And I'm going to take the difference of these two terms. I have a common 2 pi f naught, so I'll pull that out. I have a 1 here, and I have an n, so I'll take 1 minus n. For the second term, we'll have a plus, so I'll have a 1 plus n. The integral of a sine, which is going to be equal to minus 1 over the argument times the cosine of that argument. I'm going to get a minus 1 divided by 1 over 2 pi f naught times 1 minus n, and then times the cosine of this argument, which is 2 pi f naught t times 1 minus n. And then for this term, likewise have a minus 1 over 2 pi f naught times 1 plus n, and the cosine of this argument of 2 pi f naught t times 1 plus n. I also have a 1/2 I can pull out in front, and that'll cancel with the 2 that I have here, a over t0. I can evaluate my integral at the upper limit minus the lower limit. Plugging in the upper limit for t equals t0 over 2, placing that by t0 over 2, likewise over here, so t0 over 2. Then the lower limit, we're going to subtract these two terms, so we get a minus and a minus, and a minus and a minus, so we get plus signs. Then we're taking the cosine of 0 and the cosine of 0. Got some term cancellation, so let's clean this up. t0's cancel, the 2's cancel, t0's cancel, and the 2's cancel. I'm left with the value of minus 1 times the cosine of pi times 1 minus n, divided by 2 pi f naught 1 minus n, that's this term. Have the same thing again with a 1 plus n, divided by 2 pi f naught 1 plus n. Cosine of 0 is 1, and the cosine of 0 is 1. That's my value of a sub n. When n is odd, the cosine of pi 1 minus n is equal to plus 1. In other words, if I let n equal 1, I get the cosine of 0, which is 1. If I put 3 here, I get 1 minus 3, which is minus 2, which is the same as the cosine of 2 pi, which is also equal to 1. Likewise, the cosine of pi times 1 plus n is equal to 1. When n is odd, I get 1 here, I get 2 pi. When this is equal to 3, I get 4 pi, and so on, each time giving me a value of 1. So the value here would be a minus 1 and a minus 1. Have the same term here with a plus 1 and a plus 1, and same denominators. So they'll cancel, and I wind up getting that a sub n is 0 whenever n is odd. Now when n is even, the cosine of pi 1 minus n is equal to minus 1. In other words, when n is equal to 2, I have 1 minus 2, which is minus 1, which is the same as just 1 times pi, and the cosine of pi is equal to minus 1. If I were to let this equal 4, I then have 1 minus 4, which is minus 3, which is the same as the cosine of 3 pi, which is also equal to minus 1. Likewise, the cosine of pi of 1 plus n is equal to minus 1 when n is even. Let's again try that. So if I put 2 here, I get 3 pi, and that's equal to pi plus 360 degrees, and so you're just going to get a minus 1 again. So for n even, the cosine of pi 1 minus n is equal to minus 1, so I get a plus 1 divided by 2 pi f naught 1 minus n. That's the same term as here, so I get 2 of those. And likewise, this term is also equal to minus 1, so I get a plus 1 divided by 2 pi f naught 1 plus n. I get the same term again, so I've got 2 of those. The 2's cancel. F naught is 1 over t0, so that also is going to cancel with this and with this term. I'm left with a times 1 over pi, and then 1 minus n, and likewise 1 over pi, and then 1 plus n. Pull out the pi, find a common denominator of 1 minus n times 1 plus n, and multiply this by 1 plus n, and multiply this by 1 minus n. The 1's add, so I get 2. The n's cancel. Left with a times 2 divided by pi, and then the product of this is going to be 1 squared. Inner products cancel, so I get a minus n and a plus n, and then I get a minus n squared. A sub n is equal to a over pi times 2 divided by 1 minus n squared whenever n is even. Now let's go and calculate the value of b sub n. The value of b sub n in the Fourier series is 2 over t0 integral over a period of our function times the sine of 2 pi n f naught t. Our function is non-zero between 0 and t0 over 2, and our function was equal to a times the sine of 2 pi f naught t. Now here we've got a sine times a sine. We'll grab our trig identities again. Sine of alpha times the sine of beta is 1/2 the cosine of the difference minus 1/2 the cosine of the sum. Pull out the a in front, so I've got 2a over t0, my integral from 0 to t over 2, and the sine times the sine is going to be a 1/2 the cosine of the difference, and again I have the same term here, 2 pi f naught, 2 pi f naught, and I have a 1 and I have an n, so it's going to be 1 minus n, and then a 1 plus n. The 1/2s cancel with the 2 that's here, so I just have a over t0. I have the integral of the cosine of 2 pi f naught t times 1 minus n. So the integral of cosine of ax is 1 over a times the sine of ax. Take our term right here, which is 2 pi f naught 1 minus n as a reciprocal, then times the sine of the argument of 2 pi f naught t times 1 minus n. My second term is a negative sign, so I've got a minus here. And again, the same thing, the integral of cosine is going to be 1 over the argument, which is going to be 2 pi f naught times 1 plus n, times then the sine of the same argument, which is 2 pi f naught t times 1 plus n. Evaluate it from the upper limit minus the lower limit. Let's plug in the upper limits. For t, replace t0 over 2, and then likewise over here. Again, I get some terms to cancel. This cancels with this. The 2's cancel. Same thing happens here in the 2's. Then secondly, we're going to take and evaluate when t is equal to 0. So I'm going to get the sine of 0 and the sine of 0, and that's going to be just equal to 0. Now we can kind of clean up the terms and see what we have. I have a over t0, and then I have the sine of pi times 1 minus n divided by 2 pi f naught, the quantity 1 minus n. I have a minus sign here, and I have the sine of pi times 1 plus n divided by 2 pi f naught 1 plus n. Let's now evaluate the expression for b sub n for different values of n. Let's first consider n even. The term sine pi of 1 minus n is equal to 0 when n is even. In other words, when n is equal to 2, we have the sine of pi times a minus 1. And that's going to be the sine of just pi times minus 1, but the sine of pi is equal to 0. And likewise for other values of n that are even. The term sine pi of 1 plus n is also equal to 0. So in other words, when n is equal to 2, we have the sine of 3 pi, which is pi plus 360 degrees, and that's going to be the sine of pi, which is also 0. So b sub n is equal to 0 for n even. Let's consider next n odd, but n not equal to 1. We'll come back and treat that as a special case. So when n is odd, but greater than 1, so the value of the sine of pi of 1 minus n would then be, say for n equals 3, would be the sine of pi times minus 2. That's going to be equal to 0. That's the sine of 360 degrees. Same is true for the sine of pi times 1 plus n. So if n is equal to 3, you have a 4 here, so that's going to be 360 twice, and that's going to be a sine of 0. b sub n is also equal to 0 for n odd but not equal to 1. In the case for n equals 1, we have the sine of pi times 0. Of course, that's going to be equal to 0, but we're dividing this by 2 pi f naught times 1 minus n, which is also 0. So this part of our formula is indeterminate. Take a look at the numerator as x approaches 0 of the sine of pi times x, in other words, where x is equal to 1 minus n, that is also approaching 0, and likewise so is the denominator. So we can't take the limit as we approach 1 for both the numerator and denominator. What we can do is go back to calculus and use L'Hopital's rule, and that is to take the ratio of something that's approaching 0 divided by 0 by taking its derivative and then letting x approach 0 for that. So we take the derivative of our numerator, just say x is equal to 1 minus n. We would then have the derivative of the sine of pi x, which is going to be equal to pi times the cosine of pi x. And then as x approaches 0, we're getting the cosine of 0, which is 1, so we just get pi. The derivative of the denominator with respect to x would just be 2 pi f naught, and as x approaches 0, you just get this constant. So then our limit as we approach n equals to 1 for the numerator and denominator is just going to be equal to pi divided by 2 pi f naught. For the second term here, we're going to have the sine of pi times 1 plus 1, which is 2. That's going to be equal to 0. We're subtracting off 0. So that's going to just be this result, and then we've got some term cancellations again. So I have pi canceling with pi. The f naught and the t naught cancel because they're reciprocals of each other, and it's left with a over 2. So our value for b sub n is equal to 0, except for b1, which is equal to a over 2. If you look in our textbook in figure 13.4, it gives the Fourier series for a half-wave rectified sine wave, and the values that we've derived for b1, as well as a0 and an, also agree with that listed in the table. And this is supplemental problem 13.2.